All right, guys, picking up where we left off. The in keyword, in. You can use it to check to see if a string is within another string or if it's within a list. Here they've declared a string, a list called file list, right? It's got 3 elements in it. File list equals, and then square braces, my file.txt, my program.txt, your file.txt. And then they do if.txt is in file name, print the file name, right? So it's inside a for loop. I don't know why they didn't just put this into some code where it'd be easier to read, but so for file name and file list, for every file in that file list, if txt is in it, print it. And so it's only going to print the ones that have .txt in it. We can give a quick demonstration of that. So let's set it up correctly. This is lecture I, right? We're still in chapter 4. Let's define our main method, right? def main. And then let's call our main method down here, right? So if underscore name underscore equals underscore quote underscore main underscore in quote, and call main, right? Just like that. And so let's make a string, right? S is equal to hello, right? And then we're going to check to see if there's a H in it. If there's an H in S, print found the H, right? How about some letter that's not in it, like an X? If X is in S, colon, if X in S, print found the X. Now we are going to see this message. We're not going to see that one, right? And it found the H because there is an H in hello, but it did not find an X, of course. And so the slide demonstrated making a file list. So a list is a series of elements between square braces, right? 1.txt, end quote, comma, 2.docx, end quote, comma, 3.txt, right? And we're going to check to see. So for every value in file list, if.txt, end quote, in quote value, then print that value, right? And so it's only going to print the ones that have .txt in it. So we've written a for loop. It's a value-based for loop that's going to step through every element in the list, storing each one into the value variable in turn. And then if .txt is found in that variable, it's going to print it out. So it's going to print out 1.txt. It's going to skip this one because it's not in value, right? There's no .txt in it. And then it will print that one out. Guess I didn't look at that very long, but there we go, right? Found the H, 1.txt and 3.txt. All right, so it's easy to observe data crossing a network, especially in wireless networks. The attacker may be using sniffing software. Data encryption can be used to protect information transmitted on networks. One or more keys are used to encrypt messages to produce ciphertext and then to decipher that text back to its original plain text form. So example, Caesar cipher. Caesar cipher is a very simple cipher. The way Caesar cipher works is, say that you wanted to encode the word message. Well, what if you just shifted everything by one letter so that M became N, right? And E became F, and elemental P, Q, R, S, T, and T, and A became B, and A, B, C, D, E, F, G, G became H, and E became F, and S became T, right? Everything was just shifted up one letter, and now it's incomprehensible. That if you wanted to send it back, you would just do the same thing in reverse, right? What's the letter before N? M. What's the letter before F? E. What's the letter before T? S. What's the letter before T? S. What's before B? A. What's before H? G. What's before F? E. And what's before T? S, right? So we just enciphered it, and then we just deciphered it. That's a Caesar cipher. So Caesar cipher replaces every character in plain text with a character a given distance away. So example, if Caesar cipher equals 3 characters. Now, if you're going 3 characters along, right, an L becomes an M, H-I-J-K-L. So I goes to L. And then if you have N, N-O-P-Q, right, and U-V-W-X-Y, right, and A, B, C, D, and so on. And then, so when you're going to decrypt, you go backwards. So how does that work? We're going to use the Ascii values of the characters, right? And I know that I've done this before. You can go to ASCII-table.com, and you can see the values, right? And so if you had the word ABE, like Abe Lincoln, an A is a 65, a B is a 66, and an E is a 69. And so if you added 3 to those numbers, 65, 66, 69, you would instead get 68, 69, 72, right? And so you would get D, E, H, right? Because each one has been shifted by 3. A became D, B became E, and then the E became an H. So Abe got turned into, D, E, H. And then when you're ready to go backwards, you subtract 3 from it. So 68 becomes a 65, which is an A. Remember ABE. 69 becomes 66. So we get our B back. And then 72 becomes 69. We get our E. So how could we do that? Let's do that. We need to get the Ascii values out. So let's make a string that we're going to encrypt, right? In Cipher. I'm going to call it plain text, right? And it's going to say hello. And we're going to loop through it, right? So for CH in plain text, for every character in plain text, for CH in plain text, firstly, let's just print it out. Make sure that loop's working, right? So we're going to see HELLO, right? So that's working. And then let's also print out the ASCII value of it. To get the ASCII value out, you use the ORD function. Right? And so HELLO, 72, 101, 108, 108, 111. Now let's pick a shift value, right? Let's just shift everything up by 1 because that's easy to see, right? So what are we going to do? We're going to make a new string that consists of the old string shifted by 1. So maybe we don't need to print that anymore, right? But instead, we need to get, the ASCII value is equal to ORD of the CH of that character. And let's add 1 to it. Well, let's add our shift value to it, that is. And then let's add that to our new string. So we need a string to hold our cipher. We're going to start it off empty, and each time we get a new value, we're going to add it onto the cipher. So cipher plus equals the character value, CHR parentheses value, right? So this is the ASCII value. ASCII value, shift it, right? And then add to the resulting string. That's what we're doing there. And when we're done, we can print them both out, right? We could print both the plain text and we could print the cipher text. Right? And so H became I, E became F, L became M, L became N, and P became O. But really, we should probably ask for the string, right? And we should ask for the shift value. So instead of saying plain text is equal to hello, I'm going to comment that out and I'm going to ask for the plain text, right? So plain text equals input, parentheses, quote, what is the message to encipher? Question mark, space, space, greater than, end quote, in parentheses. Greater than just to tell them where to type, right? And let's get the shift value. We're not going to always shift by 1. That'd be too easy. And it's not like this is a really killer code, right? And it would take the NSA, you know, about 0.1 nanoseconds to figure out something that you sent in this. But, you know, it's a start for us to, you know, start envisioning ciphers. All right, so let's ask for the shift value. The integer value, int parentheses, input parentheses, and inside the parentheses, let's ask shift by what value, question mark, greater than, greater than, greater than, end quote. And then our two closing parentheses. All right, what is the message to encipher? Hello there, period. Shift by what value? 1. Hello there. All right. Now what if we took this string and we used it as input and we shifted everything by -1, right? So let's run it again and do that. I'm just going to copy and paste that and I'm going to shift it by -1. So that's my input. I want to shift everything by -1 and we get hello there back out. So we can run into a situation where our text looks garbled because we exceed the ASCII values of the standard ASCII character set, right? Like what if we had the word XYZ, but we added 10 to each one? And so instead of 120, 120, 122, you'd have 130, 131, and 132. Well, that's way down here in this, you know, extended ASCII code, these garbage characters, which won't even necessarily, well, they're not garbage, but most of them won't even display properly inside of idle in Python. So what we got to do is that once we get past this value, 126, because that's a control code. We never want to get that high. Once we get to 126, we want to wrap back around to a 32, right? So like if you were going to be counting these characters off, right? 123, 124, 125, 126, 32, 33, 34. So we got to check to see our value, right? And if our value exceeds 126, we need to subtract something from it to get it down to 32. So what's the difference between 32 and 127? I think it's 95. So if it's greater than 126, we're going to subtract 95 from it to get it down to here. So let's do that right here. If value greater than 126 colon, then value minus equals 95, right? We got to wrap it around to the lower values. By the same token, if it's less than 32, we have to take care. right? Because if it's less than any of these characters, we get into these control codes: file separator, group separator, record separator, end of medium, right? We don't want to try to print out any of these characters in the 31s and the 30s and the 29s. So if we get less than 32, we need to add 95 to it to get it back here. Now, if they enter a shift value that is too large, even after having subtracted 95 from it, then it's kind of on them, right? This isn't going to work perfectly. I guess we could calculate a maximum value and then tell them to, not let them enter something larger than that. But let's just roll with this right now. So if the value is less than 32, then we have to add 95 to it. So let's try it out. Let's run it again. What is the message to survive to encipher? Want A, B, C, D, E, F, W, X, Y, Z, 1, 2, 3, 4, 5, right? And we're going to shift everything by 20 characters. And here we get, right? The A turned into a U because U is 20 after A. V is 20 after B, and so on. And W, X, Y, Z, it successfully stopped it from going into those extended characters at the end, right? And it wrapped them back around to the lower part of the ASCII table, where the commas, where all the punctuation is, commas and hyphens and things. Let's take a look, right? So down here, commas and hyphens and stuff like that, in the range of 32 up to where the numbers begin at 48. Now, if we were really awesome, we could write this as a function, right? Where we do our enciphering and then we return it. So let's do that. Let's write a function, def encipher, and we're going to take some plain text and a shift value, right? And when we're done with our loop, we're going to print the shift, we're going to return the shift value, right? The cipher. Now I need to cut this and paste it up above main because I don't want to have a function defined right in the middle of main. That's not good. So I'm going to, now that I've turned this into a function, I'm going to take this, cut it, and paste it above main, right? And so down here, after we've asked for the input, right, the plain text and the shift, we can call that function, right? Cipher is equal to encipher the plain text by the requested shift value, right? This should work just as well as it did before. So what's our text? When in the course of human events, and we're going to shift everything by 15. Cool deal. And if we took this text and shifted it by -15, we'd get the original. Let's try that. We're going to call the function again, but set our shift equal to the negative value. Or we could write one called decipher that looked just the same, right? Except that we subtracted the shift rather than add it. Why not? That kind of makes sense to me. We really could write it so that we use just one function, but I like the idea of writing it two ways, right? So, okay, so here's our new function. It's going to be called decipher. And when we decipher, we're going to be subtracting by the shift value rather than adding, right? Let's add some doc strings. What does this do? This uses Caesar's cipher to code the text message or text string by the specified shift value, right? I'm going to say encode here, right? And then I'm going to modify this so that it says decode. So I'm going to copy and paste that doc string and make that say decode, right? Subtracting the shift value from the Ascii values of the string. And the other one's going to say adding the shift value from the Ascii values. Adding the shift value to the Ascii values of the string. So what were we doing here? We were just scroll back down to main, right? Let's add a comment that here. Use our Caesar's cipher functions. That's what we're doing there. I don't know why I made it green text. I'm just going to do it like that instead. All righty. Now they have a Caesar cipher code, set of code in here as well. They do it a little bit differently. Does about the same thing. They ask for the text, right? Plain text is equal to input a one-word lowercase message. Notice that they're cheating and they're asking for lowercase only. And then distance is equal to then they get the distance. I called it shift, right? Distance is fine. And here's their empty string that they called quotes. Too bad we couldn't copy and paste it because they used angled quotes. We would want to use, straight quotes. And then for every character in the plain text, get the Ascii value, right? That's what we're doing there. And then they're adding that shift value, except they called it distance, to the ordinal value. And here's where they did that thing that I said, if you get past 126, subtract 95 from it. What they're doing is they're saying is if the value is greater than a z, then subtract wrap it around starting at lowercase a. So really they're just subtracting 26 from it, right? Because if it's past a z, they want it to go back to an a. And this looks a little bit weird, but that's what they're doing, right? They could have just said if cipher value greater than ord z, which is, the Ascii value of z, then subtract 30. Excuse me, there's 26 letters, subtract 26 from it. And it's a little bit harder to read. It would have been easier to read if they'd said what I did. But this only works for lowercase text, and it doesn't work for punctuation. Well, I guess maybe it does. Yeah, it probably would. It would work for punctuation. It's more limited than ours. I like ours better. Same idea though. I just wish that they made this a little bit clearer. And then decrypting, the same business. Ask for the text, ask for the distance, subtract the value, the shift value from it. And then if it's less than an A, then add 26 to it. And you see what I mean? about it not handling punctuation correctly. If you typed in punctuation, punctuation is by definition less than the letters, right? I'm going to go and look at the ASCII chart and show you that. All the punctuation is down here in the 30s and 40s, right? With a little bit more hidden up down here in the 93s and 94s and 95s, and oh, there's a couple more here. But anyways, right? So if you typed in DOG, you know, there's a D and then an O and then a G right there. And then you typed in a period, but that period is way back here. And their algorithm would say, oh, well, that's less than a lowercase a, that's less than a 97. I better add 26 to it. And so 46 plus 26 is whatever. It doesn't work. So their algorithm, their formula here, their algorithm that they've created here doesn't work really very well. You should say enter the coded text. I don't even know how to handle spaces correctly. I don't think it would. Yeah, see, they're just entering one single piece of text here. And of course, that would actually be a lowercase l rather than an upper, because I shifted 3 values, H-I-J-K-L, right? And then they enter the coded text and they shift everything back 3 to get the original word, which again would be a lowercase I there. And so Caesar cipher worked well in ancient times, but it's easy to break using modern computers. So there are other ciphers. Using plain text characters to compute 2 or more encrypted characters using a block cipher. Each encrypted character is computed using 2 or more plain text characters using an invertible matrix. Oh, sure. Just throw that out there without any explanation whatsoever. I believe they go into a little bit better explanation of it on Cengage. But when you're doing a block cipher, tell you what, why don't we just Google that up? That's hard to read. Forgive me. I don't know why when I'm clicking it's not working. You think I know how to fix my own Wolf SSL? All right. All right, so a block cipher is an encryption method that, with the text nice and big, applies a deterministic algorithm along with a symmetric key to encrypt a block of text, rather than encrypting one bit at a time as in a stream cipher. So a common block cipher, AES, encrypts 128-bit blocks with a key of predetermined length. And then you just keep repeating your cipher over and over, the next 128 bits, and then the next 128 bits, and the next 128 bits, and so on. So do check out. Why don't we go and find it? I'm going to pause the recording and go and find it. All righty, so data encryption 4-2. Data encryption, do read this. You're cheating yourself if you're not actually reading the text. I know that reading textbooks is not always interesting. I would do so anyways. So here's one that talks about the simple encryption method, the Caesar cipher. And they're using the term wraparound for when you, oh, stop trying to do that. When you need to go past the end and reset back to the beginning, what I was doing by subtracting 95 to go from the end of the ASCII table back to the printing, the beginning of it. Here's something that they mentioned. Although it worked reasonably well in computer times, a Caesar cipher would be no match for a competent spy with a computer. Assuming there are 128 ASCII characters, all you have to do is write a program that would run the same line of text through the decrypt script with the values of 0 through 127 until a meaningful plain text is returned, right? So you could use a for loop or something to call our encrypt function, or excuse me, our decrypt function with the values, 0. I'm not sure why you'd shift at 0. You get the original input through 127, printing it out each time, right? Now, I kind of want to assign that to you for homework, so I really don't want to give you the answer, right? But you just set up a for loop. We never did call our decipher function, so let's do that. So let's do deciphered is equal to the end cipher of the cipher text, right? By the shift value, except I need to make that say decipher, right? And then we're going to print that out. Now let's add a little comment here as to what this is. This is the original text, right? And this is the enciphered text. I'm going to pad it out so that they line up. And I'm just going to copy and paste that one and make it say deciphered text, right? Like that. And we will see that it did the round trip correctly, right? It was enciphered, we made it unreadable, unintelligible, and then we deciphered it and we got the original text. All right. So what I'm going to do is I'm going to make a homework assignment where I encipher some text, and I'm not going to tell you what it is, but I'm going to give you this part of it, and I want you to decrypt it, to decipher it by writing a code that uses a for loop and calls the decipher function on it over and over and over, using that for loop. Conceptually, for I in range, 1 comma 128 or whatever, right? And then you're just going to call the decipher function with the text that you're doing, followed by I, that's your shift value, and then print it out, right? You better store that value, right? And then you better print it out, right? And then it would print out all, 127 variations of it. Because you could start at 0 like they suggested. All right, I practically gave you the answer there. I'm going to delete that. Okay, so the homework, decipher this text string. I don't like the fact that it wound up with quotes in it, so I'm going to need to pick another one. Dadgummit. All right, got one without quotes in it. That's a string you're supposed to decipher, right? I want you to tell me what it said in English text before it was enciphered using Caesar cipher. So write a program or modify the code from the lecture, right? To ask the user for a string to decrypt, to decipher, and then we'll use a for loop to call the decipher function we wrote with the values 0 to 127. Printing it out each time, right? I mean, you could hard code it, and you're not going to. You're going to use a for loop, right? But you could just do v is equal to decipher, you know, the text that you get by 1, and then v is equal to decipher the text by 2, right? You know, and you could print it each time, but instead you're going to put in a for loop, right? Rather than do it like that, right? Conceptually, that's what you're doing, though. So you're just going to have a variable that you use to count, you know, from 0 to 127. So that's going to be range, parentheses, 0, comma, 128. All right. Hope that's clear. If it's not, please text me for help. Let's keep going. I know I usually assign the homework at the end of the lecture, but we have more to cover. All right, strings and number systems. Talking about binary and octal and decimal and hexadecimal. Binary is just when you use the powers of 2. Well, that's moronic. They have a 2 here at the end. That's impossible, right? Binary means all zeros and ones, so that's wrong. I wonder what it was supposed to be. Let's ask Google to translate that to binary. We could also print it out in binary, I am absolutely sure. Did it tell us how to print it out in binary? Yeah, let's find out. Let's Google it up. Convert a number to binary with Python. In Python, you can simply use the bin function to convert a number. Okay, so that's cool. So we could ask for our number, right? Number is equal to int parentheses, input parentheses. What is your favorite number, right? Space, angle, greater than, close parentheses, and then let's call the binary function, right? B is equal to bin parentheses number, and then let's print it out, right? Print f quote, curly braces to hold our placeholder, number in curly brace in binary is curly brace B, right? End quote in parentheses. And I have a problem here. I have too many closing angles or something. Oh, they're not lined up, right? These are 4 spaces and these are only 3. My mistake. I need to line these up exactly right. Now it'll work. What is the message to Encipher? All right. Oh, I crashed because I tried to shift it by a letter rather than a number. If I was a good programmer, I would not allow them to type in bad data. But I am not going to fix that. All right. There, what's my favorite number? They were using 415, I think. And so in binary, it's 1100, 11111100. And they started it off with this 0B here to indicate that it's binary. We might not want to see that. I wonder if there's a way to suppress that. Let's look up the bin function in python.org. So bin function python.org, right? You'll find the documentation for it. Bin. If you don't want the OB, you can get rid of the OB by using format or by using this syntax where you use :B. Yeah, let's do that one. Let's do that one. Or you know what we could do? is we could just use slicing to get rid of this string, right? Use slicing to get rid of that part. So we've talked about slicing already. It's worth talking about again. If we have a binary string that looks like this, and we only want starting here and going to the end, that's pretty easy to do. So our slice would need to be not starting at 0, not starting at 1, but 2, and then going all the way out to the end. And if you leave the number off after the colon, it'll go all the way to the end. So 2 colon, and then if you don't fill in the second number, it goes all the way to the end. I need to make absolutely sure I talked about slicing last lecture. Excuse me for popping this open. Maybe I didn't. Yeah, I did, right? So going from 0 to 3 like that would pick up elements 0, 1, and 2. But if you leave off the second number, it goes all the way to the end. And as a matter of fact, if you leave off the first number, it assumes you're starting at 0. But like, big deal. It's not a real big saving to, not put a 0 there. But it's very useful to be able to say, I want to start at a specific point and go to the end without actually having to calculate the end. And that's what that syntax is for, where you leave off the number after the colon to get the slice. So I'm going to add new comments to that effect. Talking about slicing again. Slicing is using a pair of subscripts, right, to get a section, a slice, right, of a list or string. Let's give some examples. If our string is equal to, Bob Thompson, then if we just want the word Bob, we're going to start at 0. We want 1 and 2, and we want to stop there at 3. So the first name is equal to string starting at 0 and going up to but not including 3, right? So that'll get Bob. And like I said, you could leave that off and it would go up to, it would start at 0 and go out. But you can do it like that too. I think that's just as clear, right? And so when this is done, this will equal Bob. Now let's get the last name. ln is equal to the string starting at this position, which is index 4. Let's count it out to make sure. 0, 1, 2, 3, that's index 4. But we want to go to the end, right? Just like that. If you leave off the number before the colon, Python, or the slice starts at index 0. If you leave off the number after the colon, the slice goes to the end of the string or list. That's just so that you don't have to calculate what this position is. And you could do that pretty easily, right? And here's what we would have to do. If we wanted to calculate the length of it, we could. We could say starting at 4 and going up to the length of that string, right? But isn't that messy, having to do it like that? It would work, but let's not. Now, a weird thing about slicing is that you can also use negative numbers. I shouldn't say about slicing, but about indexing in general. If I said I wanted S subscript -1, it would give me an N, and S subscript -2 would be an O, and S subscript -3 would be an S, and so on. So it's just counting from the end. Python's the only language I've ever seen that did it like that. It's kind of cool. So like if we have the word, you know, S is equal to red, and we want the last letter, right? Last letter is equal to S subscript -1, right? And so in that case, it's going to equal D. And what's the first letter? It's at S subscript 0, right? And since the character position 0 is an R, that's what we would get there. So when you're talking about binary, oh, I see. No, I don't. I think that 2 that I was complaining about in here was meant to be like an itty bitty little 2, like a smaller font, like a subscript. Like that. But you would not print that out, right? And so what this means is that's 1, and this is the 2's place, so it's 1 plus 2 plus 4, 1 plus 2 plus 4, 1 plus 2 plus 4 plus 8, 1 plus 2 plus 4 plus 8 plus 16, but there's no 32's in it. There's no 64's in it. There is a 128 in it, and there is a 256. Now, how am I getting those values? It's just powers of 2. It's doubling each time. 1, 2, 4, 8, 16, 32, 64, and so on. An octal is base 8. When you're counting all the numbers from 0, 1, 2, 3, 4, 5, 6, and 7, but you don't have the digits 8, 9, or 10, right? It's only got 8 digits, 0 through 7. And then the next one after that would be 10 and 11 and 12 and 13 and 14 and 15 and 16 and 17. And then what's next? Again, it's wrapped around and gone to 20 and so on. Not sure why I started underlining there. But anyways, hope you can see counting an octal, it never reaches 8. Instead, it wraps around when it hits 7, right? It resets back to 0 and adds 1 to the next column. And so when we got up to 17, then it reset back to 0 and added 1 to the next column. Hexadecimal is when you have 16 digits, not merely 10. So you have 16, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 10 digits, but we need some more. We need a digit to mean 11 and 12 and 13 and 14 and 15. So A, B, C, D, E, and F. So if you were going to count in hexadecimal, you would go, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And now that we have exceeded, there is no letter G, so it goes back to 0 and we add 1 to the next column, right? And then we just do the same thing. What's after 1, 9? 1A, 1B, 1C, 1D, 1E, and 1F, right? And then we have maxed that out again because there's no G, it's just A through F. And so that one becomes a 0 and that becomes a 2. And each time we go look at AsciiTable.com, guess I've lost it, AsciiTable.com, we see those hexadecimal values, right, in another column. So a 32 in decimal is a 20 in hex. Well, I counted up to 20 in hex. I could prove it, right, just by coming down here and counting them out by hand, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a 10, right? That's an 11. That's a 12. That's a 13. That's a 14. That's a 15. Now, these are the decimal values. And that's a 16, and that's a 17, and that's an 18, right? So the values A through F represent 10 through 15. But if we continue to count, right? Getting there. We're 25. Oh, stop it. 26, 27, 28. We're getting to 20, right? We're at 1D, 29, 30, 31, and then our 20 is 32. And if we look on the ASCII table, we would see that character number 32 in decimal is a hexadecimal 20, and it happens to be a space, right? So a decimal 32 is a hexadecimal 20, which is an octal 40. Although to represent that it's octal, they stick a 0 in front of it. It says, hey, I'm octal. Oh, and I forgot, we were talking about slicing in order to get rid of that 0B in front of the binary number that we printed out. So I'm going to pause it and tidy up the notes just a little bit here. All right, so what did I do? I just made this say hex and decimal. And what about binary? Well, binary, you need your powers of 2. And to count up to the value 32, we're going to need, I believe, how many bits? Does it show us here? No, it really doesn't. But you need a 1 place, a 2, a 4, an 8. I'm counting on my fingers, a 16, and then a 32 place. So we're going to use 6 bits. So we're just going to count them down. So of course, binary 0 is just all zeros. 1, 2, 3, 4, 5, 6. A binary 1 is a 0, 0, 0, 0, 0, 1, right? We bump that up by 1. And a binary 2 is, well, that last digit has been maxed out because binary is only zeros and ones, so it drops back down to 0 and the next one goes up. And then 1 past that is 11, right? Well, not 11, but 1, 1. And now both of these have hit 1, so just like a car odometer rolling over at 99, those are going to drop down to 0, and we're going to add 1 to the next column. Hope this is making sense. And so when we have 1 here, that's a 1 plus a 2 plus a 4, right? And a 1 plus a 2 plus a 4, if we add them together, is a 7. So it's looking good so far. This is getting kind of tedious. I really don't want to write all of those out. We could write it as a little loop, right? We could make a loop that would print out all the decimal values from 0 to 32 and their hex and their binary equivalents. Think about assigning that to you as homework, but maybe I'll just code it, right? So let's do for value, or for an in, like number, in range, starting at 0, and we want to hit 32, so I'm going to make this 33. And so we need to get the binary version of it. B is equal to bin, parentheses in, but then we only want, we want to skip the first 2 characters, right? We want to remove, since bin returns a value like OB, you know, 110011, we want to get rid of the first 2. So we will use slicing. So B is equal to B subscript 2 colon in subscript, right? Start off at the first value and then go all the way to the end of the string. Now let's do the same thing for hex, right? H is equal to the hex value of n. Now that probably puts some weird character in it as well. So firstly, let's just print to see what we're getting. We're going to print out the hex value, the decimal value, which is n. Guess I could have called it D, all right, for decimal, whatever. And then the binary value. Maybe I'll change that to the word decimal, right? Now it's going to ask me all those questions, and I've got an error because of forgot to end a comment. That's because at the end of all this counting, I did not have a closing triple quote. Let's run it again. Hello, shift at 5. What's my favorite number? 22. All right, and there it goes. Okay, so the hexadecimal values, it's preceding by 0 and X. Let's get rid of those as well. So after we get the hexadecimal value, we're going to remove the first two letters again. H is equal to H at 2 subscript. So use slicing to skip the first two letters. And I'm going to do this here as well. Use slicing to skip the first two letters. The hex function returns a string like 0x ABC123. So we want to get rid of the 0x. So we will use slicing to skip the first two letters. Here we're at the same thing. Use slicing to skip the first two letters. Forgive me for reformatting it. I know I'm going to have to. There. All right. Now let's print it out and make it pretty. And what do I mean by that? Let's make it a formatted string. So F quote. And our placeholder H, I want it to occupy, oh, let's say 3 spaces, right? So H:3, end placeholder, in other words, curly brace. Now the decimal number, I want it to occupy 1, 2, 3, 4, 5, 6, 7, right? So decimal colon 7. And then this last one, I want it to be 6 wide. So curly brace B:6, in curly brace, end quote, in parentheses. All right, and so we have the 0 and the 0 and the 0. And maybe that's a little bit too much space here, but let's print some column headers, right? It would have been nice if it was left justified rather than right. So can we put -7 to force it to be left justified? Let's see what that does. Test for favorite numbers 5. All right, that did not right justify it. Excuse me, it did not left justify it, left it right justified. Python interpolated string left justify. All right, string interpolation is what we're using. Oh, and they don't tell us how to justify it. Text alignment. You can use less than, greater than, or up arrow to center or to left or to right justify. Oh, that's pretty neat. So I'm gonna left justify by using less than, but if I want it to be right justified, I'd use greater than. I've seen that negative used in other places in Java and C++, a couple other places. So that's why I did that. Let's see if that works. Test 5, favorite numbers 2. All right, now it is right justify. Excuse me, I keep saying that. It's left justify now, right? It's lined up against the left. So let's print out our header up above the loop, print hex space, decimal space, binary, right? And then let's print some dashes underneath that, right? Let's make it look pretty. All right, and so there we go. What if I wanted to go larger and I don't necessarily need to stop at 32? I could print all the numbers out to like 255. I would want to make this value wider though, right? I mean, I guess it's not crashing, but once it gets to the point where, yeah, if 255 would take 8 bits to do, right? Not 6. So if I was going to do 255, I might want to change this print statement to say 8 rather than 6. So let's put this in its own function, right? Define print underscore number underscore table. Like that. Let's define what it does. Prints the decimal, hex, and binary representations of the numbers 0 through 32. Let's say of the base 10 numbers, right? Base 10 is decimal. So that's what that does. What's your homework going to be? It's going to be pretty easy. It's just going to be to modify the print number table function to go out to 255 rather than stop at 32. Really, that's just one change. That's okay. I don't mind this part being easy, right? What are you going to do? You're going to change the place where it says 33 because you wanted to stop at 32 to 256. And then change that 6 to an 8. Give yourself more room. All right. Go on. So the digits used in each system were counted from 0 to n-1, where n is the base. In base 10, you have 0 through 9. In base 16, which is hexadecimal, you have 0 through 15, but really you have 0 through 9 and then A, B, C, D, E, and F. So it converts a string of bits to a decimal integer, and they give you a long chunk of code for doing that. It's a lot easier than that. I'll show you how to do it in one line of code. Well, 2, because you got to ask for the bits, right? So I guess we better call our print number table function. Let's go down here and add that to main, wherever main is, way down here, right? There's our print table function call. I need to cut this and move it above those notes because those notes are a bit ridiculous, right? There. Just making sure it works. Hello. Make sure I didn't break it. All right, still working. Good. All right, so we were going to continue on our merry way, define more code, right? More of the lecture, right? Let's get some input. We could ask for the input of the bits, right? And we want to convert that to a number. N is equal to int bits base 2, right? And then print the bits and then N, right? Guess we can make it look a little bit better. F quote binary equals curly brace bits in curly brace, comma, decimal or base 10 equals curly brace N, right? End quote. You can do the same thing for hexadecimal, right? Now, if I just type in hex equals, notice it's purple. I just broke the hex function. I wouldn't be able to use it after that in this program. So I need to come up with a better name for it, like hex digits equals, right? 1, 2, 3, ABC, end quote. And let's convert it. N is equal to int, the hex digits, comma, base 16. Convert from binary to an int, and this will convert from hex to an int. I'm going to just steal this print statement, paste it, and change this to hex equals hex digits, right? Just put a blank there to make the code easier to read. I forgot to call the function. So I got to go and put a call to more code down here inside main, right? Well, not inside main, but in a place where we're calling all of our functions. So that'll run that. Format them consistently. I'm just putting a space between the parentheses to make it easier to read. There already was one there. All right, now to work. See, whenever we write a program that asks for input, it gets annoying. All right. All right, so this number, 1100101010, whatever, its decimal value is 810, right? And then here's the hex, right? So the last bit of homework for this, well, the middle bit is going to be to take the print number function and modify it to print the values up to 255, right? The last part of the homework, write a program that works like this. I'm going to put this in green text to make it easier for me to type without having to put a hash in front of everything. So please enter the number to convert. And if you typed in 1111, right? And then is that H for hex, or B for binary? And they type in a B. And then it's supposed to print 1111 binary is 15. decimal, right? And then after you rerun it, please enter the number to convert. ABC, is that hex or binary? And this time they're choosing that it's hex, right? And it would say ABC hex is, and honestly, I don't know what ABC is in decimal, so we're going to cheat and use this little program up here to figure it out, right? I'm just going to take that, run it, watch its output. Right, and so ABC is equal to 2748. So 2748 decimal. All right, so that's part 3 of the homework. Or you could ask what you want to do first, convert from hex or binary, and then ask them the value, right? Or you could write it like this. Do you wish to convert from hex or binary? And then they choose B, right? And so please enter the binary number. Type in 1111, and then it would say 1111 binary is 15 decimal. Then rerunning it. Do you wish to convert from hex or binary? I choose hex, and then please enter the hex number. They type in ABC, and we would say ABC hex is 2748 decimal. Okay, so that's part 3 of the homework. I think the lecture is about long enough. I'm probably going to record another one and post it so that we will have 2 serious lectures this week. But I don't mind stopping at this slide. And sure, you could convert from binary to decimal using this kind of code. Would work just fine. But I'd rather use a built-in function myself. And so how integers, I said I was stopping, but I'm continuing to go. How integers are converted from decimal to binary. If I had to convert the number 62 decimal to binary, and I wasn't going to use that bin function, what you do is you keep dividing by 2 and carry the remainder. So 62 divided by 2 gives us 31 with a remainder of 0, right? And then 31 divided by 2 is 15 with a remainder of 1, right? Because it's not an even number. And then 15 divided by 2 gives you 7 with a remainder of 1. And 7 divided by 2 is 3 with a remainder of 1. 3 divided by 2 is 1 with a remainder of 1. And 1 divided by 2 is 0 with a remainder of 1. And then you just write the digits down in reverse order. So 1, 1, 1, 1, 1, 0 is 62, right? We would just take the last digit, last column, writing it from the bottom up. So 1, 1, 1, 1, 1, 0 is 62. And we can modify our code to prove that. Right, 1, 1, how many ones was it? 1, 1. I forget if it was 5 ones or what. Let's go back and look at the slide that I was mangling. 1, 2, 3, 4, 5 ones followed by a 0. I believe that's what I have now. 1, 2, 3, 4, 5 followed by a 0. And so when it prints it out, hopefully I'll see the number 62 if I did my division, correctly. Yeah. All right. And that's what this algorithm is doing on this slide. All right, I'm ready to start talking about files. This is the wrong PowerPoint. That is a PowerPoint for C++. But anyways, next we're going to be talking about reading from files pretty soon, writing to files. Oh, first I'm going to talk about octal. Okay, great. Read up on octal. I've already explained a little bit of it. So Python includes a set of string operations called methods. Well, we are going to stop here. We're going to start on page 27. So I'm going to say we made it through 126. Excuse me, page 26. So this is chapter 4 through page 26 of the PPT. All righty, hope that made sense. Hope the homework's not too weird. Should not be too hard because the examples are already in here, but if you get stuck, as always, please send me a text. All righty.